All right, today we are going to be talking about sequences and summation notation. Really our kind of home stretch of material here. We've got sequences and series, and what we're going to have in this part of the course is just going to be an introduction. There's a lot more with these that you can do when you get to calculus. You'll do that particularly in Calculus BC. So this is just an introduction. I don't think you should find it too difficult. Some of it you'll already know, particularly in the next two sections. But here we're focusing kind of on the symbols and the vocabulary that are probably new. So our first definition is for an infinite sequence, and this is the notation for infinite sequence when we have the little braces around it, and then a sub n is a rule. So it could be any rule. It could be, 2x minus 5 in the braces, and that would indicate an infinite sequence. With an infinite sequence, the function has the domain being the set of positive integers. So also known as natural numbers. So 1, 2, 3, 4, so on and so forth. When we have a sequence, the function values we name a sub and then whatever term number they are. So since our domain starts at 1, that means we plug in 1 to whatever this rule is first. So in the example I gave, 2x minus 5, you'd plug in 1 for x and you'd get negative 3. And so a sub 1 would be negative 3. A sub 2 would be what you get when you plug in 2 for x, 3 for x, so on and so forth. A recursion formula is a formula that defines the nth term of a sequence as a function of the previous term. So instead of just having a straight rule with a variable, the rule is defined by the previous term, or we should put a parenthesis s here because it could be more than one previous term. Factorial, a factorial, if n is a positive integer, then n factorial, so the factorial symbol is an exclamation point. We're not just really excited about the variable n. So we read this: n factorial is the product of all positive integers from n down to 1. So meaning if you have 5 factorial, it's 5 times 4 times 3 times 2 times 1. Because 0 doesn't fit into that, just so you know, 0 factorial is 1. So that's important to note. Summation notation is something that represents the first n terms of a sequence. And this right here is the full summation notation. So the summation sign, which is right here, which we read sum of, is the capital version of the Greek sigma. So that's what this letter is. What we have down at the bottom, this I equals 1, and sometimes we use n instead of I, or k is common as well, but I would say I, n, and k are the three most common to use. This guy is what we call our lower limit. So it's telling us what we should start when we're plugging in the values. So in this case, we're starting with 1. Up here is whatever the upper limit is. So where do I stop? So I might have a summation, and the way we read it would be the sum of whatever this rule is from I equals 1 to n. And what this means is we're going to plug in 1 for the rule, then 2, then 3, then 4, then 5, so on and so forth until we get to whatever n is. And notice, summation, sum, means addition. We're adding all of the terms together. So that's what makes it a little bit different when we have a summation as opposed to just a sequence. A sequence, we just have the set of the values, so we've got commas between them. When we have a summation, we're adding all of the terms together. All right, so looking at some examples here, example 1, write out the first 4 terms of the sequence. So here we're given an actual rule, and the first 4 terms, remember, on a sequence, the domain is the set of positive integers. So we would always start with 1 on the sequence. So that means I'm going to plug in 1, then plug in 2, then plug in 3, then plug in 4, since it asked for the first 4 terms. So 3 plus 5 times 1 squared over 1 plus 1 squared. So on the top, that gives me 8. On the bottom, that gives me 2, which simplifies to 4. Then I plug in 2. So 2 plus 2 squared on the bottom. On the top, 3 plus 5 times 2 squared. So this on the top gives me 23. The bottom gives me 6. So 23 over 6. And then we repeat. So now we use 3. Sorry, it's hard to write small with this. So 3 plus 3 squared. So bottom here is 12, top 9, 45, 48. So 48 over 12 gives me 4 again. And then my last one, because I stop at 4, 3 plus 5 times 4 squared over 4 plus 4 squared. So 20 on the bottom. 18 times 5 is 80, plus 3, 83 over 20 would be my final answer there. So this entire list is my answer, because when we write out terms of a sequence, we separate them with commas. Okay, here we're just using the alternate notation. So we could just have the rule a sub n like this, or we could have the rule in braces. This infinity means that it goes on forever. So just because it goes on forever doesn't change what I'm supposed to do here. It's an infinite sequence anyway. I'm only writing out the first 4 terms. So in this case, we have 2 to the first over 3 to the first plus 1. So that gives me 2 over, actually, that plus 1 is in the exponent. I couldn't tell at first, but it's on the same line with the n. So that gives me 3 squared in the bottom, which is 9, 2 in the top. So 2/9 for my first term. And then I'm going to continue 2 to the second, 3 to the second, plus 1. So 27 in the bottom, 4 in the top. Next, 3 to the 3 plus 1 over 2 to the third. So bottom 3 to the fourth is 81, top is 8. And final term, 3 to the 4 plus 1 and 2 to the fourth. So 2 to the fourth is 16, 3 to the fifth, I think that's 243, but let me check. Yep, okay. So 243 in the bottom and 16 in the top. So here is the answer to that one. All right, this next one has a factorial in its answer. So we have 1 squared over 1 factorial. So 1 factorial will just be 1 because there's nothing below it to multiply with. And the top is also 1, so 1 is my first term. Then I have 2 squared over 2 factorial. 2 factorial is 2 times 1, so just 2. Top is 4, so 4 over 2 is 2. 3 squared over 3 factorial. So 3 factorial is 3 times 2 times 1, which is 6. 9 over 6 reduces to 3/2. Then 4 squared over 4 factorial. So 4 times 3 is 12, times 2 is 24, times 1 still 24. So I have 16 over 24 there. They're both divisible by 8, so that gives me 2/3. All right, and we are done with that one. Example 2, find the first given number of terms of the recursive sequence. So here, it's telling us what the first term is, and then it's saying that the next term is going to be 2 times the previous term minus 3, and it wants me to find 4 terms. Now the first one's easy because they gave it to us, so my first term is going to be 1. My second term then, I take the previous term, which is 1, and I do 2 times 1 minus 3. So that gives me -1 for the second term. The third term is based on the term before it because this says n minus 1. So the term before it was -1. So I do 2 times -1 minus 3, which gives me -5. And then the fourth term, 2 times -5 minus 3, which gives me -13. And there are my 4 terms. All right, next one wants 8 terms. So the first one is 1, the second is 1. The third term is the sum of the 2 previous terms. So n minus 1, n minus 2. So that means the 2 terms before it. So I've got 1, 1. Then the third term would be 1 plus 1, which of course gives me 2. Then the next term is the 2 terms before it. So this one and this one. So 2 plus 1, which gives me 3. Then next, the 2 previous terms are now 3 and 2. So that gives me 5. Now 5 and 3. So 8, 1, 2, 3, 4, 5, 6, 2 more terms. 8 plus 5, which is 13, and then 13 plus 8, which gives me 21. Notice that on this one it said f sub 1. That's because this is a Fibonacci sequence, and so it has like a special notation because it's very well known. There's so much you can look up in our world that follows a Fibonacci sequence. It's pretty cool. So if you're bored, look that up. All right, now we are going to evaluate some factorials. And when you get to calculus, it's going to be important that you know how to manipulate the factorials. I am going to show you how to do a factorial in your calculator as well. That won't help us, of course, on the ones with variables, but it will be important that you can manipulate these for calculus and upper level math courses. So 13 factorial really means 13 times 12 times 11, so on and so forth. This means 11 times 10 times 9, and I'm just going to write times ... all the way down to 1 because we get the picture without writing it all out. Now, the reason why I wanted to write this all out and not just put it in your calculator is because I want you to understand how simplifying these factorials works. I have down in the denominator everything from 11 down to 1. So if you look up here, this part right here is 11 down to 1. And because it's separated from the rest by multiplication, that means that we can cancel it just like we would cancel out if, I had a 2 and a 4 in a fraction, or if I had an x and an x that I wanted to get rid of. So really then this just leaves me with 13 times 12 in the numerator, which is obviously a very easy problem to do. So that's how we simplify those factorials. Now, we can check our work in the calculator. The factorial button is in the math menu. So first I'm going to set up my fraction here. So alpha y equals, and I'm going to do 13, and then it's math. You scroll over to the probability menu, and it's choice 4. So that types the factorial symbol. Then I can do the same thing again, math, probability, choice 4, and then enter, and then it gives me the answer that I can check to make sure it's correct. Okay, now the calculator will not help me with this guy because it's variables, but n plus 2 would obviously be where we would start. Then we would subtract 1. If I subtract 1 from this quantity, I get n plus 1. If I subtract 1 from this quantity, I get n. So really, I have the whole n factorial times n plus 1 times n plus 2. The denominator, again, is n factorial. So these, because they're separated by multiplication, can cancel each other out. So now all I have to do is n plus 2 times n plus 1. So we can FOIL that. That gives me n squared. Outsides and insides give me a total of 3n, and then plus 2. All right, moving right along. Example 4, find the value of the sum. So when I was using the equation editor, I did not have a choice to put my lower and upper limits on the top. This is another way that it's seen. I think that your book does it the other way, but know that these mean the same thing when they put them kind of on the two ends of the sigma. It just takes up more room. Since we need more room to the right to do it that way, but that's the way my equation editor was working. So when I read this, because of course we always want to sound intelligent when we're reading math, this says the sum of 12 over negative 5 to the n from n equals 1 to 3 is how we would read that. And what that means is that I'm going to plug in 1 first, then 2, and then 3 is where I'm going to stop since it's my upper limit. Remember that this is a summation. So we don't put commas between the terms, we put addition signs, and we're going to find a final value. So start out with my first term, which is plugging in 1. So that gives me negative 12 over 5. And then I'm going to add my next term. I've got 12 over negative 5 to the second. So that'd be 12 over 25. Then my final term, because I'm stopping at 3. It's a good thing I am, because these powers get big really quick. This gives me negative 125 on the bottom. So that's going to give me negative 12 over 125. It's also fine if you want to write just a minus because you know it's negative. If we were just writing out the sum in simplest form, we would do that. Since it's really part of our work and not part of the answer, you can really do it either way when it's part of the work. But here is the sum that we're trying to find. Obviously, we would need a common denominator, but you can use your calculator to plug that in. So we've got negative, and it's 12 over 5, then plus another fraction, and second fraction was 12 over 25, and then minus our last fraction, which is 12 over 125. Enter. Negative 252 over 125. So negative 252 over 125 is our final sum, which makes it our final answer. All right, this one, we have the sum of 4i plus 2 times x to the I from I equals 1 to 4. So if I plug in 1, and I'm not going to write out all the steps this time, I've been doing that to illustrate, but I'll run out of room probably on this one. So I equals 1, that means this is going to give me 4 plus 2, which is 6, and x to the first power. So this gives me 6x for my first term. Then I'm going to add that to, next I go to I equals 2. So if I is 2, 4 times 2 is 8, plus 2 is 10. So it's 10 times x to the second. Next term would be I equals 3, so that's 12 plus 2, which is 14, times x cubed. And then I'm stopping with this term when I is 4. 4 times 4 is 16, plus 2 is 18, and it'd be x to the fourth. So this is what I get from term 1, 2, 3, and 4. None of those are like terms, but we should write it in standard form. So kind of switch the order. Sorry, that kind of looks like a 9. My pen slipped a little, but it's a 4. And so now we've written it in standard form, and that is our final answer. Okay. Example 5. These ones are the more difficult ones because it requires us to actually notice patterns and kind of think through some things. So when I look at this and I want to write it using summation notation, which means that I'm going to need a sigma sign, I'm going to need a lower limit. So we'll need n equals 1 to something, or I, or whatever, k, whatever you want to use. So the pattern that I notice is that the numerator is always 1. So if something is unchanging, you can kind of look. We had an unchanging numerator here, and that actually was the numerator in the rule. So I'm going to make my numerator 1. In the bottom, what I have for the denominator, I have 2, 4, 8, 16. You should notice a pattern with those. Those are powers of 2. Starting with 2 to the first. So if I make this 2 to the n and start at 1, then I'm going to have 2 to the first, 2 to the second, 2 to the third. My last one is 2 to the fourth, so that would give me my upper limit. So my answer is n equals from the sum of 1 over 2 to the n from n equals 1 to 4. Sometimes there could be more than one correct way to write a summation. So always, just write out, like, to check your work. You could do exactly what we did in example 4 and just write out all those first 4 terms to make sure that it's giving you the exact same thing. And if it is, then even if yours isn't the same as a classmate's or the same as mine, it's still correct. All right, last one. So pattern here. So I'm rotating between ends of 7 and 2. 2 to 7 is 5. 7 to 12, also 5. Okay, so my pattern is that I'm adding 5 every time. We're going to learn more about these in the next section, but when you have a constant difference between your terms, that is what we call an arithmetic sequence. And when we have those, whatever you're adding every time, it becomes a multiplier. So I know I'm going to use I this time since I used n last time. I know that in my summation, I'm going to have 5 times my variable. So now, typically we start at I equals 1. You can start in other places. So if, again, you started somewhere else and you got an answer that is, similar to, you got these first 5 terms to all be the same, then that's fine. I'm going to start at I equals 1, and then really it's just kind of working backwards. So if I plug in 1 for I, that would give me 5. But I need my first term to be 2, so I would subtract 3. Now I need to check it. I can't just make a guess and leave it. If I equals 2, 5 times 2 is 10, minus 3 does give me 7. If I make it 3, 15 minus 3 is 12, 4, 20 minus 3 is 17, 5, 25 minus 3 is 22. So I've confirmed that this works for all of my terms. So I just need my upper limit, which I had 5 terms, so it would be 5. And I've checked them all, so I'm certain that my answer is correct. All right, so that should give you a pretty good idea about factorials, summations, and sequences. And in our last 2 sections, we'll just discuss some specific types of sequences.